The mission of Institute for Systems Research has always been to address challenging science and engineering problems that are at the forefront of interdisciplinary research. And it really involves systems practices, systems thinking, and systems methodologies.
The ISR, or the Institute for Systems Research, started in 1985. It was one of the first 6 engineering research centers of NSF. And that was a new program that they started in response to President Reagan's initiative to try to bring academia and industry together across disciplines to reshape and revitalize the US economy.
Traditional topics and novel topics, all the way from chem biosensing to actuation and control, materials processing, fabrication techniques, energy and power considerations, integration and packaging of those microsystems, brain research as applied to, microsystems as applied to brain research, and characterization and testing. We've identified our main strengths according to the many research projects going on within those areas, and they're chem biosensing, actuation and control of tiny systems, materials discovery, and fabrication techniques. In the next 10 to 20 years, I would hope for 2 things within this area. One being really developing the systems engineering side of microsystems research and allowing much more of a systems holistic design approach to being able to develop microsystems and families of microsystems that satisfy slightly different application areas, as well as commercialization of the existing exciting technologies that people are working on.
Operations research is the science of better. What that means is essentially decision making. So something that I work on a lot is the National Commercial Aviation System. The Federal Aviation Administration, for example, has to decide every day what to do with the 60,000 or so flights that want to fly around the United States, not all of whom can do what they want to do exactly when they want to do it because they're competing with other flights for congested resources, particularly when the weather gets bad. So somebody has to make decisions about who gets to go and when do they get to go and how much do they have to wait and how do we keep that fair amongst the different players that are partnering in this process.
Control research is the understanding of the physics or the mechanisms of the system you want to control, the design of an artificial system that is going to interact with the physical system, and the implementation of that and the certification of the performance of the overall system. So the Maryland Robotics Center has 33 faculty members working in cutting-edge research in the most varied areas of robotics, and that includes medical robotics, space robotics, cooperative robotics, robotics at small scales, and interaction of robotics with biological systems.
We are all interested in networks. Most people at ISR are interested in some sort of a network, whether it's a cellular communication network or ad hoc communication network, sensor communication networks, on or in-body networks, social networks, for instance, on the internet. This concept of networks is everywhere. We do different kinds of research. Some of us look at these fundamental limits that I emphasized, which is the discipline of information theory. Information theory is interested in not only what can be done, but what is the best that can be done. Information theory as a discipline is the discipline of finding the ultimate performance limits of networks, communication networks. So information theory looks for answers to the questions as to what is the best that can be done. How many bits can I transmit through a channel at most, and how much can I take a file and compress it at most. So the field of information theory asks the question of what can we do in ultimate limits. And we will be interested in their communication and their networking. These devices will be very small, they will be moving sometimes, and they will have severe energy constraints because they will have either no or very small batteries. And they will not have an infrastructure, and we will want to network those small devices in very challenging communication channel environments. And I'm sure that these will pose new information theoretic problems for us at ISR.
Signal processing is still a very foundational area here in ISR. We do a lot of research in speech processing. We also analyze neural signals to understand how the brain is encoding information, and we also do quite a bit in forensics. The speech enhancement work that I've done is focused on improving the clarity of speech when you're in everyday noisy environments. Signals are patterns, and we develop systems to process these signals in various ways. We want to manipulate them. In speech recognition, I want to pull out the information in the signal that tells me what you said. But for speaker recognition, I'm not as concerned about what you said, but I'm looking at those features that tell me about the particular person.
So neuroscience is a very interdisciplinary research topic. It involves people with many different expertise, from computational to physiology to psychology. Some of the most exciting things happening at present at ISR in the neuroscience area include imaging of brain function. That is imaging of actually the physiological processes and development and its relevance for infant development and medical therapeutics. Imaging of cognitive function include understanding how we pay attention, how we make decisions, how we memorize things. And all of these can have implications for robotics, small animal models, and involve advances in engineering fields. When we do this work, we are always hoping that tomorrow will be the day when we understand the brain.
As we progressed, we started realizing that many of the real systems had all these disciplines in them. So if you're going to put together into a well-functional system, you really have to do cross-disciplinary research. And most importantly, you cannot do it alone. Model-based system engineering is capture our initial vision. By using models in the system, you can make the analysis and the design quantitative, repeatable, modular, checkable.
So ISR is one of the top research institutes in the world because it has such a unique collection of people in various areas, from controls research, communications, optimization, business, chemical engineering, systems engineering, and it creates a unique umbrella and support for multidisciplinary research.
The best part of ISR for me is the fact that the collection of people who work there are all incredibly talented, and they come from such a wide variety of disciplines that the set of problems that I can imagine working on grows enormously compared to what I would consider doing if I were my own research shop by myself.
Things I'm most proud about ISR are the following. First and foremost, the outstanding quality of different kind of students that we produced over the years. Second was the extensive work we have done with industry.
ISR students receive some of the best training available in any discipline, but more important, they're exposed to a very diverse group of professions and activities. Our students not only receive the best training as part of the graduate program here in this institute. Upon their graduation, they have many exciting options available to them. If you look at our record as far as where our alumni are, we cover all the prestigious universities, national labs, industries, and not only that, we try to make sure that we maintain our contact with our alumni and enable them to mentor the new students and form future contacts. So as a result, the training is combined with many great opportunities that will result as being an ISR graduate student.